Ladies and gentlemen, in this video we're going to focus on the notes and instruction that go along with creating what we call orbital filling diagrams. So this link in Unit 5 will be where you found this instructional video. Let's get into a brief set of notes and some examples to show you what orbital filling diagrams look like. So the second method of showing where electrons are in the clouds of atoms is to use what we call an orbital filling diagram, or sometimes they're called orbital filling notation. It is a more visual representation of showing the location of the electrons, but also it shows if the electron is paired or unpaired. And that'll make more sense here in a minute. It shows that it's paired or unpaired. That is extremely important to help us understand bonding and how many bonds atoms are going to make when they do bond with other elements. Electrons are represented by arrows, typically just shown with half the head, up or down, just for efficiency's sake. You'll see why in a moment, to show what side of the nucleus they're on. So if you can imagine the nucleus of an atom. We're just going to draw it as a small little positive center here. And if we have an energy level, and we have electrons that are both very negative, right? They're going to want to be as far apart from each other as possible. So if this electron is moving this way around the atom, then this one, to stay as far apart from it as it can, is going to end up moving this way. So that's how we talk about the, quote, spin of an electron, is which side of the nucleus is it on, okay? Is it on the upside or downside? And then each orbital within a sublevel is shown as a box or an underscore, okay? And each of those orbitals can hold 2 electrons, okay? So think of the S sublevel with a single orbital as kind of your sports car, your 2-seater, okay? Think of your P sublevel with 3 seats in it as kind of the, we'll go thoroughroad SUV, because we don't want to have to go full-blown minivan yet, not in high school, right? So we got 6 people who need to go on the trip with us. We're going to take the SUV. D, when it starts to get a little out of control, and you have 10 people, you're going church van right here, okay? Big family, we're going church van. And then if you really get out of control, like my mother's family with a whole bunch of people in it, then you need the short bus. So S's have 1 orbital that are shown by an underscore or 1 box. P's have 3 underscores or 3 boxes. D's have 5 or 5 boxes. And F's have 7 or 7 boxes, because they hold 2 electrons, 6 electrons, 10 electrons, or 14 electrons. Okay? Now, to be 100% honest with you, I've never done this and drawn boxes. I think it's way too cumbersome, and it ends up being far messier to do it this way than to just draw the underscore lines. Okay? One thing you do have to remember is you have to label each orbital where they belong. So typically, what I'll do is I will put marks on either side of each sublevel, like this, just to separate them as I write them out in a string. So I'll just put marks on either side like that. All right? And we'll do some examples later. I will show you what I mean by that. Now, we're still going to fill up our sublevels that are now expanded to show their orbitals, according to the Aufbau principle. So we're still going to do the filling order. When a second electron is added to any orbital, if a second electron is added to any orbital, then you need to make sure it has opposite spin. That's called the Pauli exclusion principle. In other words, you draw 1 up and 1 down arrow, never 2 positives or 2 negatives. What that would mean is that they're both at the same spot at the same time, and that's impossible. And then finally, if a sublevel has multiple orbitals, which would be the P, the D, and the F sublevels, each orbital must get a single electron before any gets 2. That's called Hund's rule. Okay, so we have the Aufbau principle, the Pauli exclusion principle, and Hund's rule. The best way to learn this, to be 100% honest with you, is to go through some examples. So we're going to take a look at some examples here together. First example is one of the ones we did in the first video on electron configurations, and we're going to go with nitrogen, okay? So nitrogen has 7 electrons in it in its electron configuration, starting with 1s, it holds 2, 2s holds 2, we have 3 electrons left, they're going to go into the 3p. So for nitrogen's orbital filling diagram, or orbital filling notation, we would draw out a single underscore line. That's going to be our 1s, and it has 2 electrons in it, so we're going to make 1 up and 1 down, okay? And then you don't have to do this in another color. I just want to make them stand out so you know what I'm saying when I talk about the breaks. We put a break in there. Next is the 2s. So we're going to draw a single orbital. We're going to label that as the 2s. We're going to go up and down. Because there's just 2 of them, there's only 1 orbital. We'll put a break in. Now for the P sublevel, it has 3 orbitals. So I want to draw 3 lines. And in the middle, I want to label that 2p. You may see in the book or online these being labeled px, py, and pz. We don't need to get that detailed, to be 100% honest with you. What I need to do now, though, is I need to show you how Hund's rule comes into play. So we have a 2p sublevel with 3 orbitals and we have 3 electrons. What you don't want to do is fill this up, down, up. Hund's rule says that in a sublevel that has multiple orbitals, every orbital must get a single electron before any of those orbitals gets a second. Okay? So that would be a correct and complete orbital filling notation or orbital filling diagram for nitrogen. 1s2, 1, 2 electrons, 2s2, 2 electrons, 2p3, 1, 2, 3 electrons. Let's take a look at chlorine next. Take a look at chlorine. Okay, and chlorine has a electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. That gives us 17 total electrons. Again, we're going to start with the 1s. We're going to label it. We're going to go up, down, and then we're going to put our break in. Next comes your 2s. We're going to fill that up, down, put our break in. Next comes your 2p. This time, though, if we look at our configuration, 2p has 6 electrons in it. So we're going to give every orbital in the 2p sublevel and up a single electron. And then, if we have enough, we're going to come back and fill it up until there's no more room. Remember, each orbital can only hold 2 electrons. Each one gets a single electron, according to Hund's rule. When we go back and start pairing them up, we make sure that they are heading in opposite directions. We're going to put our break in. Next, after 2p, comes 3s, so we're back to a single orbital. We're going to fill that up, down, because it said 3s2, so that's filled. And then we have our last sublevel for this one, which is 3p. So let's draw our 3 lines in. Okay? And now we have 5 electrons left. So according to Hund's rule, we're going to give each of these a single electron. And then we're going to go back and pair up until we run out of electrons. In this case, we're going to have to also deal with Pauli exclusion principle, meaning we have to place the remaining 2 electrons. So 3p5, 1, 2, 3, 4, 5. That last one's going to be open. Now, all we're doing is we're expanding out our configurations, and we're showing the electrons a little bit more visibly. This is important because these unpaired electrons, they are bonding sites. They are places where another atom's electron can come in and overlap here, and they can share 2 electrons between their orbitals, and that's how we end up creating bonds. That's how we end up creating bonds between atoms of different elements, or even atoms of the same element. I want to do one more that's a little bit longer, so that I can show you the D's. We'll go with lead here. We'll go lead that has an F sublevel. This is going to be a little bit longer, but it's intentional so that we can actually see what do we do, first of all, when we run out of room, because we're going to, and then secondly, what do we do whenever we have the F and the D orbitals, and how do we label all of this? Pretty much the same way that we did the S's and the P's here, but we're going to have a few more lines to deal with. So we have 82 electrons to put into orbital filling notation, so we're going to have 82 arrows. For lead, we're going to start off same place we always start with the 1s. It gets an up and a down. We'll put our block in, or our break. We'll go 2s. It gets an up, down. After 2s becomes 2p. You can draw these a little bit skinnier to try to save yourself some room as well. Following Hund's rule, every one of them is going to get a single electron before any of them gets doubled up, and when they do get doubled up, we're going to apply the Pauli exclusion principle and make sure that they have opposite spin. 3s is going to be filled up and down, so 3s2, it's filled. 3p6 is going to be filled, so we're going to do 3 lines for the 3p. Up and down. Sorry, I should have done Hund's rule, sorry. We should have gone up, 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 then down, down, down. Now, to be 100% honest with you, if you know it's filled, you can fill them up, down, but I would really get in the habit of doing up, 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 and then pair them up, okay? That'll just help you so you don't do something silly if you run out of electrons here at the end in an F, P, or a D sublevel. 4s comes next. It's full. We can do up, down because that's only a single orbital. Now this is where you have to be careful. After 4s comes 3d. So remember the D has 5 orbitals. Make sure you label that. Hund's rule. Everybody gets a single before anybody gets an opposite double. That's Pauli. Alright, there's our D. And then we have our 4p after that. Give yourself 3 lines. We can go up, 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 down, down, down. That's the end of our 4p. Now, obviously, we're out of room. So, continue on with the next row. Give yourself a little bit of space. I'd probably skip a line. After 4p comes 5s. 5s is going to get filled up and down. We're going to put our break in. After 5s comes 4d. So give yourself 5 lines. Fill them all individually up. That's Hund's rule. Pauli exclusion. When we fill them up, with partners, they're in the opposite direction. Put in your break. After 4D comes 5P. Hund's rule, everyone gets a single. Before opposite spin poly, they get a double. After 5P, we get 6S. Okay, 6S we can fill up and down. What comes after 6S? The 4F. Now, this is where we gotta do 1, 2, 3, 4, 5, 6, 7. 7 lines. Now, 4F is full, so we're gonna go up in each of those 7, and then down in each of those. I'm sorry, that line should have been blue enough. Alright. Okay, so what comes after 4F? 6S, 4F, 5D. We're going to get singles, and then we're going to pair them up opposite. That's applying Hund's rule and Pauli exclusion principle. And then finally, we come to the end of our string. We have a 6p2. Now, even though 6p only has 2 electrons, up and up, you still have to draw these, all 3 of those sublevels. Always draw every sublevel, every orbital, even if it's an empty one. Okay? Never skip drawing. So if it's a P, it's always going to have 3 lines, whether they're used or not. You could have 1 electron in 1 orbital. You have to draw all 3. If this F was a 4F1, you would have to draw out all 7 lines and put a single electron at the beginning. Alright. At this point, I've gone through really the longest example we need to go through with lead. You can go ahead and jump into the assignment piece, which will be below the video. So if you exit out of this video, you should find your assignment and the instructions on what to do for orbital filling notation. If you have questions, I'm probably still on the conference if you're doing this during class. If not, you can do your best and then ask questions tomorrow in our conference.